Welcome to the next lecture in engineering materials. Till now, we went through basics, classification of materials, and in this lecture, we will try to see majority of them on non-ferrous structures or non-ferrous materials. Content, we will have a brief introduction, then we will have key characteristics, then classification of non-ferrous materials and alloys. Majority of the classifications which are there, I have put aluminum, copper, zinc, nickel, lead. Titanium is also there, but I have just given you a glimpse of all the spectrum of material. Finally, you will have a small recap. When we move out of iron carbide diagram, or when we move from ferrous material to non-ferrous material, cast iron is one element which is very predominant. It has been used in the past for several applications, like utensils have been made, the base has been made, and statues have been made, right. So, cast iron have been there for quite some time. When the industrial revolution happened, many of the machine beds were made out of cast iron. For several applications, they said toughness is very good, it has lubrication property, all those things were there. So, now let us try to understand what is this cast iron and where does it come from. When you go back to the iron carbide diagram, if you see carbon content more than 2.15, I will put it here somewhere, right, it is 2.5. So, 2.15, anything about 2.15 to somewhere around about 4.5, right, this area is called as cast iron. So, the difference is iron, you try to diffuse carbon, you keep on diffusing carbon, it becomes cast iron. Okay. So, when you see a blacksmith, what he does is he tries to put a steel and then he puts all around coal and starts burning coal. So, many a times what happens when the coal starts burning, the iron gets into red hot condition, there is always a diffusion of carbon from the charcoal into the iron. So, that is called as Fe3C. So, ferrous carbide, right. So, this is Fe3C is a compound which is formed or an alloy which is formed by the diffusion of carbon into iron. So, the cast iron are the ferrous alloys with the greater than 2.14 weight percentage of carbon, but typically containing 3 to 4.5 weight percentage of carbon. So, it is not only carbon, there are other alloying elements which are also added like silicon. So, this tries to control the kinetics of carbide formation. So, when I said C here, iron cementide, Fe3C cementide, right, Fe3C is cementide. So, you can see here Fe3C is formed. Okay. So, these alloys have relatively low melting point, do not form undesirable surface films when poured and undergoes moderate shrinkage while solidification, that thus can easily melted and amenable to cast. When we take metal to a molten state, then when it is poured into a die or into a mold, it will always demonstrate a property of shrinkage. If the shrinkage is very large, then it becomes too difficult to control the geometry of the output. Whereas here, the interesting part is the cast iron alloys have relatively low melting point, do not form undesirable surface films. What are the surface films? Like oxidation getting formed, a slurry getting formed, or a sludge getting formed, or a thin layer on the top which is getting formed, which is undesirable, because when you try to pour it, this fellow also tries to chip in along with the material and gets into the mold or in the die, creating a defect. So, cast iron does not form any undesirable surface film when pouring, undergoes moderate shrinkage while solidification. The cast iron which is also called by an acronym Ci, is a type of iron that contains more than 1.7% carbon, usually in between 2% and 4.5%. The pig iron is a mixture with the scrap of iron and steel to produce cast iron. So, generally the cast iron is produced in a cupola furnace. Cast iron is the cheaper metallurgical material available to engineers. Stainless steel and all needs refinement, right. In the process of generating iron, the pig iron, from pig iron to cast iron, they all go by that. When carbon is reduced more and more or refined more and more, you get mild steel, low carbon steel and stainless steel. Cast iron are hard and brittle. So, they will be always used at the base. So, there will not be much of elastic load or fatigue load on them. There are multiple types of cast iron. The ferrous cast iron is obtained between 2 to 4.5% of carbon, which is called as Ci. So, the list of Ci is grey cast iron, white cast iron, mottled cast iron, malleable cast iron, spheroidal cast iron, sponge cast iron, chilled cast iron and inoculated cast iron. So, you have different types of cast iron. We will see one or two of them in detail. So, the strength of cast iron, if you see, so the y axis is a plot of stress and x axis is a plot of strain. So, in the x axis you can see the plot of strain. So, when you look into it, you can see the cast iron ultimate tensile strength is around about 200 or 250. So, 250 MPa. Okay. The tensile strength is around about 250 MPa. The compressive strength is around about 1000 MPa. So, here it is tensile load and here it is compressive load. When you try to stretch the cast iron, you will try to get 250 megapascal. When you try to compress them, you get 1000 MPa. So, it is very clear cast iron can be used for compressive load. And here the strains, if you see, it is round about 0.005, and when you see in compressive, it is 0.065. So, what happens is it tries to bulge and then it tries to break. Right. So, the shear modulus is around about 51 GPa, the compressive stress is around about 1000 MPa and the tensile modulus is around about 110 GPa. The Poisson's ratio value is around about 0.17. So, it is good for compressive as compared to that of tensile. The grey cast iron are generally obtained when Ci is cooled slowly from the molten state. So, temperature is the only game changer who tries to bring in all these modifications. So, slow cooling leads to grey cast iron. The combined carbon then has time to separate out and to remain present in free carbide form. So, what happens, when it is slow cooling, the carbon will have time to get separated out and it will remain as green graphite forms. The grey cast iron has low tensile strength because of the presence of flakes. What do you mean? So, suppose you have a piece and you have flakes. These are all graphite flakes. So, naturally when you see these places, there is a discontinuity in the material. So, it will yield or it will have poor tensile strength when you try to pull it. Strains, right. Presence of graphite flakes at the crystal boundary. The grey iron has the grey fracture surface. When you break it, it will try to give a grey color. So, that is why it is called as grey cast iron. Has a grey fracture surface with finely faced structure. As I told you, Si is added to promote carbon flakes precipitates rather than carbide formation. If the carbide tries to diffuse into iron, it forms carbides. If it is not allowed, then it forms this flakes, graphite flakes. So, these graphite flakes, graphite has a very good lubricating property. So, it has self lubricating and absorbs vibration and has good resistance to compressive load. It can be used in cast form only and is not suitable for hot or in cold work due to a high carbon content. When you try to work, hot working, cold working and all, it does not happen. It can be welded, but it is very difficult. It contains flakes formed of graphite whose tips are sharp corners. So, due to sharp, these are the sharp corners, the sharp tip, they become source of stress concentration leading to failure. Grey cast iron are very strong in compression, which we have already dealt. It gives you a grey color, that also we have discussed. Graphites are formed instead of carbides. It can be given to any desirable shape. The only thing is you should be very careful with surface to volume ratio. The surface to volume ratio, that means to say the volume of the material should be sufficient enough as compared to that of the surface area. Since the graphite is an excellent lubricant, the grey cast iron can be easily machined. However, brittleness lead to a lack of ductility and poor shock resistance. Always tries to put a limitation of this material in engineering use. This is how the grey cast iron looks like. The structure is marked by the presence of graphite. You can see here, these are all graphite. In the microstructure, the black image is of graphite flakes and the white image is of ferrite matrix. Ferrite is iron dominated. The graphite flakes are about 0.05 to 0.1 millimeter, that means to say 50 to 100 microns in length and approximately 10% of the metal volume. So, the white cast iron, it comprises of cementite phase. Grey is graphite, white is cementite. The white iron has a characteristics, white cast iron, they also call it as white iron. The white iron has a characteristics of white and a crystalline fractured surface. They have a large amount of Fe3C formed during the casting. It is very hard and brittle. Moment you have more of cementite phase, it is always going to increase the hardness. So, wherever you want to have a wear resistance property, moving surface, you want to have a wear resistance property, you would prefer to go for white cast iron as against that of grey cast iron. White cast iron is obtained by Ci cooled rapidly, grey slowly, Ci cooled rapidly leads to cementite. That means to say there is not, it tries to move inside and freeze and the carbon does not get time to separate out. So, it moves inside iron, it is frozen. It is hard and brittle. It can be machined, but not like using a heavy depth of cut. For example, if you want to chisel and make a statue, it is very difficult to make using a white cast iron. It is easy to make on a grey cast iron. A white cast iron have a more even distribution of carbon within its structure and is heated for a prolonged time in the presence of iron oxide to reduce the carbon. So, it is used for producing malleable cast iron. In the presence of cementite, it is extremely hard. So, now we saw hard. Next, let us see malleable cast iron. It is produced from white cast iron, that is the source, on a prolonged heating at 900 degrees Celsius followed by a slow cooling. So, you have already formed a white cast iron, where in which you have not given time, enough time for the carbon to move and then form graphite. Now, what you do is you take that and then you do a prolonged heating up to 900 degrees Celsius and then you do a slow cooling. Due to this process, cementite whichever is formed tries to decompose into ferrite and the silicon which is kept is less than 1% so as to avoid graphitization. So, silicon also plays an important role to avoid graphitization. So, then this cast iron becomes easy for doing malleable operation or ductility operation. In malleable cast iron, the edges of the graphite flakes as a stress risers and the heating process changes the shape and the size of the flake, making material more ductile and malleable. So, it is cheap and a substitution of steel forging, and it is used for pipe fitting. In those days, you can see malleable cast iron pipes were made for big pipes were made. The pearlitic malleable cast iron has an increasing manganese content up to 1%, which will act as carbon stabilizer and improve the shock resistance property. So, because of this, it has been used in agricultural machinery as well as pipe fittings. So, grey cast iron is used for base, white cast iron very hard, malleable cast iron which is used for making machinery and implements, so that it can take toughness as well as it is better than cast iron. Spheroidal cast iron, spheroidal, spheres, right, spheroidal or nodular cast iron. It contains graphite in the form of spherical nodules. So, what was like this in the grey cast iron, now it is going to be made into spheres. Since there are no sharp edges in these spheres formed, the condition of stress risers does not exist and the brittleness is unnoticed. So, if at all you have a crack, the crack goes here and then the crack goes around the spheroidal nodule and then it continues. So, there is lot of relaxation of stress whatever is there. The spheroidal cast iron is produced by adding Mg or Ce to the molten iron. The content of Si is up to 2.5%. It has a good casting property and a better mechanical property. We always go for spheroidal cast iron when we are trying to make a bell or something like that. The spheroidal cast iron can be partially hot or cold worked, machined or welded. It is a good substitute for steel forging. It is used for crankshaft, pump casing and gears, etc. Spheroidal graphite cast iron was used in the initial days for water mills or wherever we had a gear, heavy gear, bull gear, wherein which they had in opening and closing of a gate, they used spheroidal casting. It was very heavy. The pump casing was also made out of it. Wrought iron. The wrought iron is refined pig iron, where the carbon content is very low, less than 0.1% and usually approximately 0.02%. It is the purest form of iron. Why do you need the purest form of iron? You need it because after that you can start playing with the properties. It is produced in less quantities because it is relatively high costly. So, you have a nascent material. From the nascent material, now you add whatever you want, silicon you want, magnesium you want, manganese you want, cerium you want, anything you want, you keep adding to it. Right? So, wrought iron is very ductile because it has low carbon content. So, the carbon is the king player there. It can be easily worked, although machining is very difficult. It is tough and it also has corrosion resistance property. It is used in those applications where a visual warning of failure is required, such as link cranks, where overload causes a considerable increase in the length of a link. So, slowly it will get stretched because it has ductility property. Wrought iron is a mechanical mixture of pig iron and uniformly distributed silicated slag. It has the important property of ductility, malleability and toughness. I am sure by this time you will be able to distinguish ductility property and malleability property. It is suitable for machine parts. It has an excellent welding property. Why is that welding property every time talked about is because when you want to make a large massive structure, it is too difficult to make through casting. So, you will make small pieces and you will try to join. So, when you try to join, welding becomes very important process. So, whether the material is allowing to join similar material or similar dissimilar material. Now, let us move into other non-ferrous alloys. The other non-ferrous alloys are aluminum, titanium, chromium, copper, magnesium, nickel, cobalt, lead. All these things are other non-ferrous alloys. They also play a very important role depending upon the requirements. Non-ferrous materials are metals and alloys that do not contain iron in significant amount. Maybe few traces can be there. It's not that Fe will not be there. Fe traces will be there, but predominantly it will not have iron. These materials are distinguished by their unique set of properties. We will see the unique set of properties in the coming up slide. Their corrosion resistance property is very, very important, which makes them ideally used for a harsh environment. It can be making a container in a saline atmosphere, it can be underwater tank or something, it can be swage tank. All these things are corrosive environment. Their lightweight nature is critical in industries like aerospace and automobile. Additionally, electrical property and thermal conductivity property ensures their use in the electrical systems, electronics and renewable energy technology. Today what we are trying to do is, when we try to make a holder, electrical conducting as well as strength giving member. So, if these two can be blended together, then it gives a wonderful property as well as lightweight. Where it will be used? For example, kettle, the electric kettle has to be lightweight, it has to be corrosive resistance, right? It has to have electrical property, and it also has to have this thing thermal conductivity. So, all these things are to be brought in one place. So, non-ferrous material are non-magnetic so that enhances the suitability for sensitive application in electronics and precision instruments. See, non-magnetic property is very important. When you try to pass current through a coil, it will try to generate EMF. So, this EMF or electromagnetic induction, so this will try to hamper the performance of the nearby equipments. So, the non-magnetic properties are very important. Their malleability and ductility allows for complex shaping and forming. This highly recyclable material, compared to cast iron alloys, this non-ferrous alloys are easy in recyclable materials, because the temperatures are very low and you can have a better control. These highly recyclable materials maintain the quality through repeated cycle. So, the first time you recycle, still you get the almost a similar property. So, contributing significantly to sustainable practices. Due to the versatility property, non-ferrous materials are crucial in advanced technology in construction, energy, transportation, healthcare, marine engineering, and solidifying their position as a fundamental component in modern engineering and technology. So, more and more materials are used today are non-ferrous material. So, when you look into all the alloys, zinc alloy, aluminum alloy, magnesium alloy, copper alloy, chromium alloy, titanium alloy are all there. So, each of them finds their own niche in their own areas. For example, bronze, brass, copper combination, aluminum, then you can have nichrome, titanium Ti6 Al(V4), beryllium copper, right, nickel, then you will have copper nickel, then you will have niobium. So, when we talk about aluminum, the primary ore of aluminum is bauxite. It is a sedimentary rock that contains minerals like AlOH thrice, gamma AlOOH, alpha AlOOH, Al2Si2O5OH4 and FeOOH, Fe2O3, TiO2 and FeTiO3. So, these are all the part of the sedimentary rock like bauxite, where they try to use it as a starting raw material and then they try to refine it and get aluminum. So, aluminum has multiple properties and these properties can be common for almost all the non-ferrous alloys. Lightweight, except for certain, for example, lead alloys are heavy, but apart from that they are all lightweight. Aluminum is lightweight, low density, making it one of the most lightest material. Corrosion resistance, because it quickly forms an oxide layer on the top which protects it from corrosion. Malleable and ductile, it can be given a shape and it can be drawn into a wire. High strength to weight ratio, high strength to weight. So, because it is lightweight, for this lightweight whatever strength we have is very high, then it is recyclable. It finds its application aluminum, titanium, magnesium, all these fellows find a huge application in the aerospace industry, automotive industry, construction industry, electrical industry and packaging industry. All of these three, aluminum alloys, titanium alloys, magnesium alloys, they almost have very similar properties like this. So, when you talk about aluminum alloy, so it is always Al 3034 or 6061. So, aluminum will always be, aluminum alloy will be always given a code. So, this code represents the 1x, 2x, 3x, 4x, 5x, 6x, 7x. So, it is this x is given. So, this is 1, 2, 3, the base number 1, 2, 3, 4, 5, x is the other 3 combinations, right. So, depending upon the aluminum alloy 1x, 2x code, 3x code, here they are finding lot of applications. Generally, we will try to prefer aluminum 6x code, because which finds lot of application, or 2x code, right. 2x is 2021, 6061, something like that. Right. So, aluminum magnesium alloys, wherein which 5 to 10% of magnesium is added, 90 to 95% is aluminum. This is exhaustively used for making aluminum wires. So, lightweight with high strength ratio, excellent corrosion resistance, good weldability and formability, non-magnetic, resistance to stress, corrosion, crack, etc. It is non-toxic, so it is finding lot of application. When we see aluminum alloy, duralumin, which is 4 to 5% of copper, 0.5 to 1% of magnesium, 0.5% of manganese, and 94 to 95% of aluminum alloy. Age hardening for increasing strength over a period of time happens. It gives superior stress and impact resistance. Age hardening is a phenomena which will be dealt in the heat treatment discussion. Lightweight with exceptional strength, high toughness with very heavy loads. These are all the properties of duralumin, which is finding lot of applications in aerospace industry today. Then aluminum silicon alloy, so it also finds lot of application. Better castability for complex surfaces. It has a very high wear resistance in high stress usage, corrosion resistance in humid as well as in salty environment, low thermal expansion for dimensional stability. These are all a combination of aluminum with silicon. Aluminum with copper, 3 to 5% of copper is mixed with aluminum. So, 95 to 97% of aluminum is there. High strength, fatigue resistance with moderate corrosion resistance is there. Ensures structural integrity in demanding applications. Tailored via heat treatment for various needs. So, aluminum copper is also finding lightweight. This is for conductivity. Right. Maintains high strength at elevated temperatures. Let us move to the other alloy, which is copper based alloy. Copper based alloy always gives excellent electrical resistance and conductivity, which is generally not so high with aluminum. It has corrosion resistance, forms a protective patina on top of it, highly ductile and malleable, allowing easy to shape. Copper is easy to shape. Brass and bronze are all copper based. Non-magnetic, making it suitable for several electronic application. Antimicrobial property and reducing bacterial growth on the surface is done when you have copper based alloy. That is why we use copper bottom flask and other things. Easily recyclable with without losing lot of quality. Brass, which is a combination of zinc and copper. So, 60 to 90% copper, wherein which 10 to 40% can be zinc. It is malleable and ductile. We make brass statue, small Murti statues, whatever we make of God or Sardar Vallabhbhai Patel or whatever it is, malleable and ductile, Mahatma Gandhi. High strength to resistance to corrosion, exhibits a gold like appearance, very important, gold like appearance, and it has good machinability property and thermal conductivity. Brass statues are very famous, brass utensils are also very famous. Bronze, bronze is a combination of copper and tin, 88 to 95% of copper, 5 to 12% of tin, 0.5 to 6% of aluminum, 1 to 4% of silicon, 0.5 to 5% of Mn, and 0.01 to 0.35% of phosphorus. All these things mixed together to make it a very beautiful material for making intricate statues. They are all made out of bronze. High strength and hardness, it excellent corrosion resistance, especially in sea water. So that's why when you see, when all these murtis are given wash with varying material, for example, water, then some honey, this, that, whatever, milk they do, the pH content of all those things keeps changing. But still, doing multiple times whatever it is giving an exposure, still the statue is able to retain because of its excellent corrosion resistance. Resist metal fatigue and wear, can be cast into intricate shapes. Moving towards nickel, nickel bronze, which finds excellent application in marine fittings. Okay. So, here it has high corrosion and wear resistance, especially in seawater. Suppose water tank, along the coastal tank, they always have these types of valves which are made out of nickel bronze. High strength and excellent mechanical properties are there. Excellent resistance to oxidation and high temperature. Suitable for bearing as well as marine application. In marine, we always use for nickel bronze as the material. Nickel chromium alloy is also there, which has 50 to 70% nickel and 15 to 30% chromium. Chromium means it is resistance to corrosion, high temperature strength and oxidation resistance. So, that means to say, if you make a nickel chromium alloy gear and if you expose it to 300, 400 or even 600 degrees Celsius, nothing is going to happen to the shape and size of the teeth. Right. So, it has oxidation resistance, superior mechanical properties in extreme conditions. When there is a high temperature application, nickel chromium alloys are used. Magnetic properties depends upon the composition, ideal for high temperature applications such as turbine blades. The other important application of nickel is going to be Inconel. Inconel has primary nickel with chromium, iron and molybdenum, titanium, aluminium and the other elements depending upon the specific alloy. Inconel 625, Inconel 718, these two are used exhaustively in aerospace, in turbine blades, in marine applications. Retain strength at very high elevated temperature. For example, in thermal power plants or in turbines, wherever gas turbine, all these places they exhaustively used Inconel. It is slightly heavy as compared to that of aluminum, but it has a very high temperature resistance property is there. Performs very well in harass environment. Its resistance to deformation under high temperature, resist deformation under high temperature stresses. It has a good weldability property. So, Inconel finds lot of applications: aerospace, power generation, flanges, chemical processing, marine, jet engine, turbine blades, exhaust systems, gas turbine and high temperature applications. Right. So, Inconel finds lot of usage nowadays. Lead has high density and malleability. It is soft and easily moldable into various shapes. It has excellent corrosion resistance. Its toxicity and environmental concern limits it to certain application. It has poor mechanical strength and high temperature. That is why it is used exhaustively for electronics application. As you know, lead is very soft, but very heavy. Lead tin alloys, which has 90 to 95% lead and 5 to 10% of tin. They are soft and malleable with good corrosion resistance. They are exhaustively used in batteries, non-toxic in some application, but toxic in others. Selectively non-toxic applications. Low melting point, which makes it ideal for soldering and widely used for electrical and electronics soldering purpose. It has very good electrical properties, soft material. Zinc has a very good protective resistance, zinc coating, galvanizing, zinc coating, right. So, protect from rust, especially used in outdoor and industrial environment. It is suitable for die casting and alloy production. It has various used in zinc is used in various application. It has good thermal and electrical properties, such why it is used in electronic materials. It can be recycled very easily, where in which the properties are maintained. Zinc alloys. So, this is zinc aluminum alloys, 85 to 95% zinc and 5 to 15% of alloys. So, they are exhaustively used for making nut and bolt for required applications. High strength, good casting property is there, excellent corrosion resistance when galvanized, high fluidity in casting, it is cheaper than other strength alloys. To recap what all we have seen in the 3 lectures, whatever it is there, 1, 2 and 3, the purpose of studying different engineering material and its application was dealt. Different types of ferrous and non-ferrous material with examples of each was seen. The properties of metals and its application was dealt. We also introduced composite materials. The key advantage of composites over traditional material was also discussed. The role of different tool steel in engineering material was seen. Different types of cast iron in engineering material and use of alloys were dealt with. These are the references which we have gone through. Before I close, I would like to give you a assignment which you don't have to submit. You don't have to submit, but an assignment for you after undergoing all this basic understanding, how do you make a proper choice of material? Let's take 3 examples. 1, let's take a nut and bolt which is used for temporary joining. Okay. Next, let us take a tumbler which is of high aspect ratio. 3, let us try to take a plate. Okay. So, these are the 3 examples. Now, what do I want is, I want you to make a table like this. Okay. In that table, what do you do is, you will try to choose 3 alternative material. For example, you can choose polymer, metal and ceramic, or you can try to choose in metal, you can try to have ferrous, non-ferrous. Right. So, you can try to have a table. So, for each of these things, right, when I say a plate, which is for a dining plate, nut bolt, it is basically for joining. So, you can try to see what are the alternatives I can have for the same application. For example, you can't make a nut and bolt out of ceramic. So, then what I would suggest is, you should try to take under metals, you will try to take 3 different categories. One is stainless steel, or the other one is you can take aluminum, and the other one you can take Inconel, whatever it is. You can choose that, and then what you do is, you list down all the properties which are very important for this application, and for this application. For example, tumbler should have corrosion resistance property, tumbler should be light in weight. If you decide I will make by polymer, it is okay. Then you please justify all the reasons. When you try to do it under metals, for example, I will do a stainless steel, fine. I will do it as something else, fine. And then when you try to have a tumbler, where sometimes you will also drink tea. So, when you drink tea, it will have, if the thermal conductivity is very high, it is difficult to hold. So, you will try to look for a low thermal conductivity. So, then you might go to polymer, or you might go to ceramic as glass. Okay. So, this exercise will try to give you one application, what are all the possible different types of material I can choose. And after you choose, what are all the properties which made you to think that this is the best choice. That is what I want through this exercise. You do not have to submit to me. When you do it with sincerity. List down all the mechanical properties, all the physical properties, and then start filling it. When I say physical, it is going to be density, electrical conductivity, thermal conductivity, these are all physical. When I say mechanical, you will try to talk about ductility, all these things, right. So, you make a table and that will try to give a very good knowledge about this lecture, whatever we have done. With that, thank you so much for your patient listening.